Thank you very much for this really nice introduction. First of all, it's a pleasure for me to be here. We have classrooms with 200 students, but they never show up at the same time, so I'm also very happy to see that many people. My background is applied cryptography. I do research on sensitive data and how to protect them in untrustworthy environments like cloud. But when I was thinking about what to talk about this cloud computing security and privacy field, I said, let's do something nice, because there are two different things I want to mention tonight. The first thing is integrity, which is an industry-driven problem. It is handed over to the researchers, so I think I have to mention this. It will be the first part. And the second part is, as promised, about homomorphism and how to use homomorphic encryption schemes for secure computation, which is more futuristic topic for us. It will be challenging in the sense that the second part is a little bit mathematical, but please, as suggested before, just ask me any questions if you have any. Let's start with the first part. This is the cloud computing infrastructure. Who is working with cloud computing one way or another? Can I see some hands? Wow, that's amazing. Who doesn't work? Okay, good. Well, this is a picture we are using in my research or in my group's research. We say that, okay, we have people using cloud computing, but most of the time those are the end users. End users, one way or another, they generate data. Those data are then collected by the service providers, and most of the time service providers are delegating this responsibility to cloud environments. Why? You know it better than me, because there are so many good things about using cloud computing environments. But if you take a look about the roles and their obligations or responsibilities, we have the server with computational resources, and their responsibility is to respond to the request by the clients. And they also have a state to protect, maintain a state. Clients, as you can imagine, they request an operation from the cloud service provider. They also need to verify the computation, and they might partially maintain the state. And we always assume that response is correct most of the time. This is a perfect environment to align my research with reality, so please forgive me if I ask too many questions. Any of you, did you have any problems with verification of the responses received from the cloud environment? Verification itself. You do some computation and you don't trust the result. Anything like that happen to you? No, perfect. Well, the thing is, in terms of this setting, we have three major problems. The first one, verifiable computation. Apparently, this is not a problem for here, but it's very important because most of the time, big entities or big institutions, they delegate this responsibility of computation to the cloud because they have the computational resources. And we assume that the computation is correct. How can you verify that? You cannot verify because you don't have the computational resources. But you have to verify the computation. One simple example. You have a data set of 10 million entries, and you want to compute the average value of these 10 million entries. And you are a malicious cloud provider. What would you do to make more money, to save from computation and space? I will definitely run the algorithm for 1 million entries, return the result, and the client wouldn't even see that. What is the difference between finding the average value of 1 million and 10 million? In terms of clients, he cannot or she cannot check this. So verifiable computation is extremely important where you're outsourcing the computation to the cloud. This is a research field, very active. The second one is integrity. You have uploaded all your sensitive data, commercially valuable data, privacy-sensitive data to the cloud, and you assume that it is safe there. How do you verify that? How do you check that your data is there? Any opinions?
We have certificates that we think prove something.
Certificates. That's a good motivation. But how can you detect that the data is not there or the data is there? So this is the second research field in this domain, checking the integrity of the data. Many times we say that a cloud provider is malicious in terms of they want to delete a part of the data because they need space, but there could be some software or hardware failures as well. Because of those mistakes or errors, you might lose some data. You should be able to detect that as a cloud service provider. So integrity check is very important. And of course, if the data is coming from several resources, several writers, consistency is a very, very challenging task. Imagine that you're using Dropbox, one file, everybody's editing. Well, it works really fine at the moment, but if there are several writers concurrently writing on the same time, which one is the lost state? And how can you verify the correctness of this maintaining the state of the data? And this is the third field, very, very important for industry as well as researchers at the moment. Of course, I cannot talk all about it, but I need to dive into integrity to give you a small, tiny clue about what is being done. If you go into details about integrity, well, data is very important. We upload it to the cloud environment. We are happy because whatever happens, I know that my data is safe there. That's really nice. But how can I prevent anyone, including the cloud provider, from tampering the data, right? Intentional or unintentional mistakes, errors, behaviors. So this is the purpose of integrity research, and we have a setting for that. We assume that there's a writer, this is the owner of the data. It has the data, and he also computes an authenticator, a message, a digest of the huge data set. And this authenticator information is reported or sent to the readers, one reader or multiple readers. The data, authenticator, and the state of the data is also stored by the cloud. Writer cannot respond to the queries from the readers because they don't have, or he doesn't have any resources to do that. Cloud is the responsible entity. When the reader starts asking questions, cloud provider will give the answers, but once in a while, a reader will ask, hey, I'm looking for this block of data, but I also need a proof that it does exist and it is intact. It was, or it is as it was sent by the writer. So this query will generate a response, and the response involves or includes a proof from the cloud provider showing that this block is the same thing sent before by the writer. And of course, this verification procedure should be extremely efficient. I can imagine that you are dealing with huge amount of data in the order of terabytes, petabytes. Computing an authenticator verification procedure should be really, really efficient, regardless of the size of the data. How would you do that? The very simple approach, not a simple, but the basic approach is using authenticated data structures. Listeners with a computer science background should know about data structures. This is yet another structure, but it is the authenticated version. What does it do? We have the data, you compute a data structure, and these data structures let you compute an authenticator, a signature of the whole data you have, and this authenticator will help you to verify the integrity of the data later on. How to do that? There are several ways, but the most important, or the basic one, is Merkle hash tree. You have blocks, really large amount of data, You sort them out, and the approach is very simple. Of each block, one by one. Anyone knows hash functions? Who doesn't know? Please just... We know, okay, great. So hash is a digest of a input, arbitrary length of input is fed to the algorithm, and you get a small digest. Each block is used to take the hash, and the hashes of two blocks will be, again, hashed, and you build a binary tree. At the end, you will have one single root, and this root is the authenticator. You give this value to the readers, and if one reader wants to check the integrity of the block, 2 in this example, Cloud will provide a proof. What is that proof? Actually, the proof will consist of block itself and the hash values required to compute the root. Why? Because as a client, I have the block from the Cloud. I can compute this value, hash 2. I receive that as a proof from the server, Cloud server, so I can compute this one, and with the help of the proof, I can also compute the root, and I will check it with the one sent by the writer. If it's a match, it means that block does exist, and it is still intact. Perfect. Really nice. Do you see a problem here?
You don't know about the other part, but you haven't answered the question.
That's also very good. Why? We were asking one block at a time, so it's problematic. But if you think about your background, computer science background, this is a binary tree. Inserting and deleting blocks requires to update the whole structure, because the authenticator itself is just one single value, and it's the root of the huge tree. So is it efficient? This is the discussion. Merkle hash trees are very basic, they work, but they have a limitation because append operations, insert operations, and delete operations on data require update of the whole tree or big part of the tree, and this is not efficient. So we need much better options. Just to illustrate, when you need to append a new block, you need to compute a new part of the thing, and it is logarithmic, yes, but you need to do that for every single block, and this is not efficient. Furthermore, if you want to insert something in between, it means that all the blocks on the right side of this part should be updated. It is pretty heavy. And we are talking about petabytes, terabytes of data. The worst case is, of course, putting some block here. It means that you need to compute the whole binary tree from the scratch. As a result, there are other authenticated data structures that are very efficient in insertion and deletion operation and append. One recent, very recent authenticated data structure is actually from a Dutch student from MIT. And he came up with this sec hash, but it supports very efficient append operation, which is extremely nice for the blockchain, Bitcoin. So if you are interested, please find me during the break and I can explain how it works. But this is the thing. Depending on your data, what kind of operations you have, you need to choose a suitable authenticated data structure. So this is the first part. I believe
This was the easy part, right?
it was the soft part. But it is the goal of the researchers to come up with extremely efficient authenticated data structures that supports dynamic operations based on your application model. If you don't have any questions, I can, yeah, please.
I could imagine another way to check the integrity of your data.
Sure.
Which would be similar to the way you correct turbulations in the air when watching stars. You could insert random errors in your data that you know of and retrieve those values, and from those you could induce whether the data has been tampered with.
Very smart. One of the existing approaches, so inserting some special blocks in your data sets, retrieve a part of the data and check if the special block is still there. Yes, that's one good idea. But what about the efficiency? Yes. But it's a good idea, and it was proposed before, and I think there are some applications, but it is a linear complexity because the number of blocks you need to insert really determines this integrity check capabilities. But it's a good one. The second part of my talk is actually my expert field. It is processing encrypted data. Let's start with some questions. Who knows about homomorphic encryption schemes? Well, but there's 1, 0, or 1. Sorry?
I know the word.
You know the word. Actually, people were talking about these homomorphic crypto systems processing data for smart grid security to businessmen, people from other places, and they said, oh, there's this gay encryption scheme. No, it's not gay, but it is homomorphic. I will explain it in a short term. But I assume you know RSA, right? RSA. RSA.
Oh, RSA.
Yes, encryption scheme. Yes, it's also homomorphic. Well, let me start with this information sharing infrastructure. This is a very generic thing. In the past, we had really this amazing system, server and client model. We had one server, one client, and everybody was happy. We needed secure communication between those two entities, and you were trying to protect your communication against external entities, and everybody was happy. We have digital signatures, hash values, MACs, and encryption schemes. But now the world is changing rapidly. We have now online services, perfect, for millions of clients, customers. And they have a local database or a set of database or distributed database. But what is happening right now is those services are gathering together saying that, hey, if we combine our forces, we can do better. Do you have any example of that in your business? That you need to work with your competitor or other entities? Yes? Do you have an example of that? Which domain? Construction. Yes, that's a good one. Well, I think if you're in the finance, fraud detection is very important. And every bank tries to do that locally, but if you combine databases, you can see that you can detect fraud cases much more efficiently. And information sharing in terms of intelligence, finance, health, logistics is getting more and more important. That's why I have this ugly figure saying that these different service providers are trying to combine their sources, either the data sets or the algorithms or computational resources, one way or another. Then what is the problem? If everything is so nice, it works efficiently. The problem is security, but more privacy. Privacy is defined as this individual privacy, individuals having this sensitive data, but it's not only privacy sensitive, but commercially valuable data as well, like transactions. What is happening is that server-client model, Alice and Bob, and Alice is running some shop, and in that shop there's a camera, and there's a customer getting into the shop, and she captures the face picture of this person. She's working with the police department. She sends this information, face picture, to the police authorities. They have a criminal database, right? A database containing the pictures of the criminals. And Alice gets a call or a response saying that, hey, this is a criminal or not, right? So this is happening at the airports. hospitals. In London, in every street, there's this camera, surveillance camera. You can also scale it up using this cloud computing environment, so it's huge. The problem is the authority here, it can be the police department, but it can be also an ICT company. They have amazing amount of information. What is that information? About the individuals they are checking. It is the information that shows the location and time of the people in the pictures. So it is possible, if you have a server like this that everybody is trying to use, you can identify and track people. So it is really scary in terms of personal privacy. So secure processing, secure data processing was proposed like 10 years ago to solve this problem. The idea was, okay, let's encrypt our input in such a way that it's possible to manipulate it under encryption, but without seeing the content. The authority can process it, still cannot see the content. The algorithm produces the output, still encrypted. The output is sent back to the owner of the data, and owner decrypts it using the decryption key and sees the result. This is a perfect system for security, for privacy. Privacy because the sensitive data is completely protected from the authority, and the maybe commercially valuable algorithm for face recognition is also protected from the client. So everybody is happy. But it's really difficult. Why? Because we rely on cryptography, which is extremely difficult to break if you have limited computational resources. It's also very good because it's easy to prove that the information you leak is limited. You can set this epsilon security, but it's really, really expensive. I imagine that you are using encryption in your daily life at business. One algorithm is advanced encryption standards, and the other one is RSA. Do you know what is the difference in terms of computational resources they require? Advanced encryption standard is a block cipher. It operates on block, on byte levels, and operations are really fast. So you can implement it like this. RSA, asymmetric crypto system, relies on mathematically difficult problems, and for them to be secure, you need to work with huge numbers, big prime numbers. How big? Can you imagine how many bits you need to generate? At the moment, the prime number should be 1024 bits, so that RSA modulo should be 2048 bits. So it's huge. And if you encrypt a single image, pixel by pixel, using RSA, you need to wait 4 hours, right? So what is the thing? This idea of processing encrypted data is really cool. It's secure, it is privacy preserving, it is needed, but it is very expensive, so we need to make it scalable and efficient. Is it clear what I'm trying to tell you? Okay, cool.
But it is not certain at all that it could work at all. It depends on the properties of the sort of algorithm.
That's true. Could it work? Because we need to design an algorithm, right? Either some signal processing, speech recognition for Siri or face recognition, and it's complex operations. So in this part, I'm going to try to show you that it works, but not in a straightforward way. I think there was a question here.
He doesn't want to
Not
anymore.
Okay. If you have basic operations, like addition, subtraction, multiplication, and division, you can design an algorithm, right? But now you have a crypto system that enables you to do 1 or 2 operations, and you don't have the operands, right? Because it's encrypted. Data processing, or secure data processing, is all about coming up with algorithms that works with encrypted data. We have common operations: addition, subtraction, multiplication, division. Using those 4 operations, you can also design comparison, division, right? Comparison, quantization. And if you have all those operations, you can design any system. Fine. But one simple example for this night is you have 2 values. Imagine that there's a cloud server running for genomic data processing, and they are looking for strings, substrings in the huge DNA sequence. And the DNA is itself encrypted, but you want to know if a certain string is in the DNA or not. Definitely you need a comparison operation, right? But if the data to be compared is encrypted, it means that you don't have the content, but you have 2 random looking data. How can you check which one is bigger than the other one? First, homomorphic cryptosystems. What is this homomorphism? Homomorphism means that a set of operations in one domain corresponds to another set of operations in the other domain. Bear with me. This is additively homomorphic cryptosystems. What we do is we have 2 values, A and B. We encrypt them, and we get the encrypted A and encrypted B. Those brackets are abused form of encryption, and we use the public key for that. If you apply a certain operation on those ciphertext values, they correspond to a new encryption, but those encryption is the encryption of the original messages added. So when you decrypt it, you will get A plus B. One operation on ciphertext corresponds to another operation in the plain text domain. So this is the formal definition of homomorphism. It works. We have those systems. For example, Paye crypto system from 1999 is additively homomorphic. If you encrypt them and multiply the ciphertext, after decryption, you get the summation of those 2 values. And when you add up, you can also subtract. And if you add up with itself constantly, you can scale the value. That's normal. Let's see what we can do. Imagine that you want to compute this equation, right? But what you have is not A or B, you have the encrypted A and encrypted B. You can translate this operation to work in the encrypted domain by having the encryption of A and take the power of 3 here, exponentiation, which corresponds to a scaling operation here. You can take the power -1. It's an inverse function which corresponds to minus operation, subtraction. And additions become multiplication in the ciphertext domain. So this is doable. It's not a magical, but it's doable. It shows us that if you have a homomorphic encryption scheme, additively homomorphic, you can design linear systems. With linear systems, what you can do? You can do basic operations like correlation computation. You can also design linear functions like filtering of an image. Those are basic algorithms that you can really compute with addition, subtraction, scaling, and inner product computation. What is the catch? I don't need to decrypt anything. But gentleman with the previous question was completely right. Crypto systems, homomorphic crypto systems, gives you only 1 or 2 operations. Have you heard about fully homomorphic crypto systems? It was a big thing in 2009 because a researcher now working at IBM Watson came up with the first fully homomorphic crypto system, Craig Gentry. He showed that one single encryption scheme can also support addition and multiplication at the same time. So you can add and multiply. With additive homomorphism, you cannot obtain the product of 2 values. It's not possible. The catch with Gentry was that it was a proof such systems do exist, and IBM is extremely happy because they want to come up with the encrypted operating system that works with encrypted data, so that will solve all our security problems, and they're working really hard on it. But do you know what the problem is with the fully homomorphic crypto systems at the moment? They are impractical. Because of the construction, only key generation takes 3 days. And operations on those big numbers in the order of minutes or hours. So they are not practical, but there are at least 11 groups in the world, including the CWI. They are working hard on coming up with a practical homomorphic crypto system. If they can achieve that in the upcoming years, I hope so, then we will have the first operating system that can work with encrypted data only. Then it will be good.
The cryptographic security of the data, because when you are able to perform all those operations on it, then sort of it gives away its own semantics.
Yeah.
And that is a fundamental breach of its security.
That's true. You are very sharp tonight.
Other nights he's only a nuisance, but tonight he's okay.
Well, crypto systems are tested based on some security assumptions, and they are being used based on those, let's say, certification. For example, RSA, textbook RSA, you cannot use it in practice. You need to apply padding and randomization. Crypto systems like these are not well appreciated in the crypto world. That's true, because you can manipulate the data without realizing it. You send something to the other side, and on the way someone can insert something, and you don't even realize it. But there are other measures to deal with this. You can use, for example, integrity check, or MAC values, or digest, to check if the data is processed or not. So those things do exist, but they are also expensive to deploy. But it's a really good point. Well, thinking about the time I have, I will just tell you that with at least additive homomorphism, you can design linear systems, but you can also come up with more complex operations, but those operations will be interactive games. For example, with additive homomorphism, you can add up several values, but you cannot multiply them. If you need multiplication, you need to run a game. And it's an interactive game between the decryption key owner. That is why this field is very expensive, in the order of 1,000 or 10,000 times more expensive than any plain text version of the algorithm. And comparison protocol is just one of them. If you want to compare two encrypted values based on the additive homomorphism properties, you need to design a game which is called multi-party computation in our domain. You can do it. It's amazing. It works. We can design face recognition systems or signal processing operations, but they will be expensive. I was hoping to explain you all those tricks, but I think I need to skip all of them. But since I'm here, please let me introduce you this problem. Have you ever heard about Yale's millionaires problem from your computer science days? The question is very interesting. We have 2 millionaires. Anyone here? We only need 2.
Only crypto millionaires.
Yeah. They want to know which one is richer than the other one. But they don't want to reveal how much money they have. So this is from 1982. Andrew Yao came up with this. They don't trust each other to reveal how much money they have, but they're really interested in which one is the richer one. So this thing, computation of a function with secret input, is possible. It's doable. It's expensive, but based on these primitives, basics, you can design any algorithm, signal processing or data mining or any algorithm you are using in cloud environments, but it will be expensive. We have done lots of research on this. I'm going to skip that. Just an example, even for test environments, the encryption is expansive operation, and we are dealing with asymmetric crypto systems which introduce this huge data expansion. For example, if you want to encrypt a simple 8-bit pixel value, the outcome is 2048 bits, and you need to operate on that. That's the expensive part. But let me show you some numbers. If you design a comparison protocol, which is a basic operation for any data processing algorithm, right? And you want to test it in terms of efficiency, 10,000 comparisons with encrypted data. This was, let's say, in 2012, 93 seconds. Combined time of server computation and client computation. So 10,000 comparisons. How many comparisons can you do in the same amount of time with just plain text? In the order of millions, maybe, with a simple computer. And last year, we improved this significantly, and we reduced to 41 seconds. It looks good, 50%, but we are not there yet. So efficiency of those algorithms, protocols, cryptographic protocols are not there yet. So that's why people, when they hear about homomorphic crypto systems, they say, hey, whoa, stop there. We cannot use that. What is my takeout message for this short talk? Cloud computing is coming, and we are using it almost everywhere. Even in institutions, knowledge institutions, we use cloud for storing our data. It's really useful. But there's this integrity problem, especially for companies, for industrial companies, and this should be addressed carefully. If you have huge amount of data to be stored in the cloud environment, you need to really check for integrity. The second one is trust, verifiable computation, and secure computation. You really need to use crypto. There's no other way. So those are the two different things, but they boil down to the same principles. Cryptography is a solution, not can be a solution, but is a solution. Of course, researchers, we don't have a toolbox you can use it right now, but we are getting there. Fully homomorphic crypto systems are expensive, but we also have somewhat homomorphic crypto systems. They are okay. We can do something for you. Apart from that, if you look at the problems in the domain of cryptography, in the past, we need signatures, we need authentications, credentials, but we have now a new world with distributed computing. Maybe there's no central authority. This server-client model is not there anymore. And we have challenges like, okay, scalability, efficiency in terms of runtime and bandwidth. And of course, we have a huge trade-off between security or privacy, plus utility and overhead. So it is really difficult to achieve all of them at the same time. So you need to do some kind of a sacrifice. So this concludes my talk for tonight. I would like to thank two of my students with the preparation of those slides, but I also would like to thank you for your attention.
En wie had er nou nog een vraag? Ik vond het indrukwekkend om te zien wat er allemaal kan, maar ook wat er niet kan. Dus ik ben blij met de introductie in deze hele voor mij nieuwe wereld. Dankjewel, Zekeriya.
Yeah. Oh, thank you very much.